And I'll start with this one. What are the most promising new strategies for targeting GPCRs beyond orthosteric ligands? And if you know me, you know the answer already. I'm a big proponent of allosteric systems. And the reason I am, our GPCRs are nature's prototype allosteric protein. She designed these things simply to be allosteric. Everything they do is allosteric. Agonism, dimerization, everything. So all the equations, all the energies, vectors, and so forth are common. They're all an allosteric system. Now, the history of it is we were in an orthosteric world because the screening was finding. This is now years and years ago. And you would use robots and so forth to get high numbers screening, but it's orthosteric. Allosteric really what was hampered. To do proper allostery, you need function, because so much of allostery goes beyond the molecule interacting with the protein, but rather translating the behavior of that protein, and that's read by a cell. As soon as we started to be able to screen large numbers of compounds in functional assays, screens, and somewhere I have a graph of this with years, all of a sudden the number of reports of getting screening allosteric compounds soared, because now we have the eyes to see. When we did our GSK program for HIV, we were looking for a chemokine CCR5 inhibitor, and we did a screen, and it was binding. We were lucky, but out came a compound. And it gave us all sorts of complex profiles. We didn't know what we had until finally we realized it was allosteric. Once you know that, everything changes. The point is, you can say, well, what if I don't want allostery? Allostery will seek you. Don't think that you can design an allosteric screen and get more compounds, but there's a good chance any screen is going to give you an allosteric. So it behooves you to understand it, understand how to develop it, and so forth. So that's the long answer to allosteric. Really has exploded. The number of approved allosteric drugs right now is only about 6 or 8, but the list that are in phase 1, 2, and 3 is huge. There's a lot of allosteric compounds coming down. I'll add a proviso. The other thing is the understanding that molecules can change the disposition of receptors from inside the cell, outside. It just changing where it signals the ER, beta-arrestin kinases. That has exploded too, and simply because we now have assays. So the types of molecules that are now coming out for GPCRs, chaperones, and other kinds of compounds go beyond what it used to be, which was agonist and antagonist. That was it. Now we're exploring many behaviors. So those are the areas I see as being exciting and new.
Wonderful, Terry. I do have actually a follow-up question based on what you just mentioned. I feel like nowadays, when we think about biased compounds, we're thinking about small molecules. I think the world of antibodies is still trailing, and the world of antibodies is mainly focused on antagonists. There's some agonistic antibodies, but where do you see that moment of having antibodies that are allosteric modulators?
Oh gosh, there are some already that exist. There's no reason why an antibody can't do everything a small molecule can do. It's just a really sticky, potent, persistent ligand. And so there are now, and I thought you were going to venture into the bias question. I'll just add a quick comment on that. I have been asked, should our program seek bias? And the answer to that's easy. You don't have to. It will seek you. It is a natural allosteric outcome of the behavior of all GPCRs. In fact, don't expect your ligand to be non-biased. It will be in some way. Now, in some cases, it's extreme, and you can go off on that. But there's really don't think that bias is such a unique property that it'll derail your program. I tell programs it's happening anyway. So if you ignore it, you're walking away from potentially useful data. You may as well look at it, check it out, and see if it's something you want. Having said that, antibodies, there are known biased ligands in terms of antibodies. So it's not restricted to what kind of compound you have.
That was going to be my follow-up question. You mentioned bias, and then we can move on to the next question. That was going to be exactly my next question around bias. But let's approach the biased antibody or the antibody therapeutic function from a different manner. You will find these, I agree with you, but can you program these from the get-go and say, we are going to create biased antibodies? Or you have to test what you have and then say, oh, well, with everything that we've created, these are biased, and not the other way around.
Yeah, there are basically two approaches to exploit bias. There is the idea that you design it. I know I want a compound like this because the physiology tells me so. Now, the very first bias compound that went into humans, TRV-120, was made in Duke, and the group there had an idea. This was made for heart failure. Basically, it's an improvement of losartan. And so they had a preconceived theory. And in articles, you'll read about this. There are lists of these where someone had a bright idea and said, now I want knockouts are frequently used. Reported one is opioids depress respiration, but less so in a beta-arrestin knockout mouse. So you might want an opioid that biases away from that. The other way it's done, and the more common way and the easiest and cheapest, is cross-screening. You run a screen, get your hits, and then take those hits and cross-screen them in a different kind of assay. And I guarantee you will get a scattergram. You will not get correspondence. Why would you do that? Well, historically, you would say, I'll take my most potent compounds out of my screen and I'll advance them into complex assays like an animal. When you cross-screen and you get exemplars, compounds that are clearly different, what do you have? You already know that these molecules are making different active states. So you have selected molecules that are already known to be different. Well, the chances of finding a unique phenotype in a rat or mouse or some complex assay must be higher with those compounds than if you took all your most potent ones that could all be doing the same thing and running those. So you cross-screen, take the exemplars, and that's you move on. So those are the ways I would suggest that any agonist program, at a minimum, you need to look at bias. And there's I'll just end with this. You can either have a multiple G protein type of assay like TruePath, or minimally beta-arrestin and G protein. You might say, yeah, but I don't know which I need, and all that is telling you it's identifying a molecule that's making a unique active state. You may not know what it means yet, but you're able to pick it out. And then you test it in whole animals or other systems, and you might see a unique phenotype. I'll stop there.